Hello, sure, yes. So yesterday we saw an introduction and a motivation to matrices. So we said that these are just square or rectangular tables of numbers that we usually enclose by square brackets. We say that we have the size of a matrix, that is the number of rows times the number of columns. So this is what we mean by size. And yesterday we got familiar with a bit of the basics operations of matrices, so how to add together or subtract matrices, the matrix vector multiplication and the multiplication between two matrices. We started looking at matrices that have a special form like identity, the null matrix, diagonal, and so on. And the first hour was dedicated to like introduction to the three main pillars that kind of summarize the application of matrices. So we saw that they are useful to store coefficients in a system of linear equation, to store information about how different entities are connected in a graph or a network. And we saw a different example of symmetric problem and not symmetric problem. And finally, there was a last application that is a bit more geometric, so how we can use matrices to represent operations on vectors, such as easy case of rotations and reflection. And today the plan is to focus on this. So see how we can solve linear system of equation using performing operation on matrices. And we have the so if we have, so Sari is asking about the recording, so that's maybe Zan will answer. So if we have a linear system of equation, so let's say that we pick m equation in n variables, in the variable xi, xn. This is the usual form of a linear system, and we can actually rewrite the system using a matrix of the coefficient. So we have the matrix A that again is size m times n times applied, let's say, to the vector x that lives in R to the n. So it has n entries, so the same number as the column of A. And we get as an output a vector B that instead lives in R to the m. So it has m entries like the number of rows of A. So we can rewrite it in this way, and this is what we call, A is called the coefficient matrix of the system. If we add one column, so if we consider instead of just the matrix of the coefficient, also the vector B, this is what we call the augmented matrix of the system. So we have, so when we talk about a linear system, there are two different matrices associated to that. One is the coefficient matrix and the other one is the augmented matrix of the system. And they will, both of them come up when we try to solve linear systems. So asking whether we have a solutions of our linear system is the same. And so hello, so we were supposed to start, so hello, Kuratelan, sorry again for the pronunciation. We were supposed, it was supposed to start at 1, so at 13, at least Amsterdam time. And then we didn't have many participants, so we are really going slowly. And I decided, given that we're really such a small group, to just comment on my notes, so I'll probably be a slightly quicker lecture. So we are discussing solutions of a linear system of equation. We introduce, there are two matrices that we can consider, the matrix of coefficient, or if we add one column, the vector B, then, here, great, thank you, Kurat. B, then it's the augmented matrix of the system. And asking whether our system of linear equation admits a solution, if there is a solution X, a vector X that solves the system is equivalent of asking whether we have a vector x that we said lives in R to the n, such that when we apply the matrix A to this vector, we get B. So this is saying this is like equivalent to finding a solution for the linear system. Is equivalent to us asking this. And if we look at it in terms of possible operations of our, let's say an operation on our vector, let's say that we start from xi and the operation is the multiplication given by the matrix A. So we want to multiply A by the vector x and arrive to the vector B. So we're asking, given a certain B in a matrix A, does it exist an element that is mapped onto B via the multiplication by A? And there are different ways of phrasing that, and the final way that we will use, basically we said that when we are multiplying a matrix and a vector, the vector that we obtain is a linear combination of the column of the matrix A, where the weight or the coefficient in the linear combination are given by the entries of the vector x. And so solving the system, we're asking basically if we can write B as a linear combination of the column of A, where the coefficient are the xi, xn, the entries of the vector x. And what we are trying to do is solving the system. This might not be possible in general for certain choices of B and matrix A. You might not have solution. If there are no solution, we say the system is inconsistent. And if there are solutions, then we say instead that the system is consistent. And of course, if you have a consistent system, then you might ask, how many solutions do I get? Do I have a unique one, or I have many solutions? So these are the typical questions that we are trying to answer. First, understanding if you have a consistent system or not. And if you have it, then how many solutions, and can we describe the solution of the linear system? Can we reach a general description? And we're not going to have time to discuss that in detail, but if you remember at the very end of the exercise session yesterday, we said that if a matrix admits an inverse, so a square matrix, it only makes sense to talk about inverse if you have a square matrix, so a matrix for which you have the same number of rows and the same number of columns, then we say that the matrix is singular if it does not admit an inverse, and somehow the property of A being singular is connected to have not a unique solution. So you have a unique solution only if your matrix is not singular. And we are not going to have time to discuss more in details about that, but I invite you to go over the references. So again, the references for the talk are always the one that I put at the end of my first slide and first series of slides in the lecture of yesterday. So the lecture notes by Margot Gerritsen and the book by Gilbert Strang, Linear Algebra and Application. So there you can find more about that. Any questions so far? So this is the idea of somehow the basis of linear algebra. That's what you have: understanding system of linear equation, finding if there are solutions and how many do we have, and working with the associated matrix, the coefficient matrix and the augmented matrix. Let me pause for a second in case there are some questions. And what is the goal? I mean, in general, we want to find ways to solve the system in an efficient way. Remember that we said even yesterday that, I mean, we can do things by hand if you have a low number of variables and a low number of equations. But in general, the problems that arise in engineering, in science in general, they might have thousands, if not millions of variables and equations. And so, of course, you would not solve them by hand, you would solve them with a computer. And so you need to really have efficient algorithms so that in a reasonable amount of time, you arrive to have a solution. Or you arrive first to determine whether your system is consistent. And if so, then have an explicit description of the solution set. So by solution set, we really consider all the vectors that are solution of the systems. So this is what we are trying to do, and the lecture of today focus around one particular algorithm, one of the easier one, that is the row reduction algorithms. So arrive to first something that is called the echelon form, and then the reduced echelon form. So let me go quickly over the algorithms, and then I'll explain an example step by step. Again, I'm going a bit quickly because, again, we are not that many, so probably will be a slightly shorter version, and I will give you this set of lecture notes. But if you have any question, I'm happy to stop and go slower. So what is this echelon form? So echelon is actually a term that comes from, it's a military term. It stands for a formation that has this kind of step-like pattern. So the one that we see here in the matrix that I draw. And we say that a matrix is in the echelon form if it satisfies certain conditions. So the first one is that all 0 rows, so here, for instance, we see these are 0 rows, so all the entries are 0, lie below non-zero rows. So this one, here we have at least some non-zero entries, and so this is the first non-zero row. And all the 0 rows lies below. So if there are 0 rows, they are below the non-zero ones. Then below a leading entry, so a leading entry is the first non-zero entries, and below that you only have zeros. So like this is the leading entries for the first row, and below you only have 0. This is the leading entry for the second row, and below you have only 0, and here for this other third rows. And then the final condition is that the leading entries lies in a column that is to the right of the leading entry above it. So for instance, if we take this one, this is the leading entry, the leading entry above it is this one, and this one lies to the right, in a column to the right of this one. It doesn't necessarily need to be right adjacent, like for instance, this one lies in a column that is not right next to the first one, but is still to the right. So this is what we call a matrix in the echelon form. A rectangular matrix or a square matrix is a special case that satisfies this condition. And the reduced echelon form, it has some additional conditions. So it's still an echelon form. So it has to satisfy all the criteria for the echelon form, but then we have some extra requirement so that the leading entry needs to be 1. So in this position here, I need to put a 1. And every leading entry is the only non-zero entry in this column. So if we have a reduced echelon form, here I should have a 0, and here I should have zeros. Question on the two definition? Okay. Let's see some examples. So the first one is an example of a matrix in the echelon form. So we see that there is 1 0 row and lies at the bottom. So it's up below all the non-zero rows. Then there are 3 leading entries in this case, and below there are only zeros. And we see that every leading entry lies to the column that is at the right of the leading entry above it. And why do we care about the echelon form? So we use the echelon form to understand if a system is consistent or not. In echelon form, it's not necessary to have a square matrix. No, kurat. So it's not necessary. So even here we have this example here, and this is a rectangular matrix. So it doesn't need to be a square matrix. And we we'll use we can use this to understand if the system is consistent or not. When this form is used, so that's what I'm explaining now. So you want to use it to understand if the system is consistent or not. So let's assume for a second that this one is that this matrix A is the augmented matrix of a linear system. So assume that A is the augmented matrix of a system. So what does it mean? It means that the last column is the known vector B, B1, B2, B3, B4. And it means that I have, in this case, 3 equations, because the last one is only a 0 rows, 3 equations in 1, 2, 3, 4 variables, right? So the first equation would be x2 plus 3x3 plus 4x4 equal 5. And then the second equation would be 3/4 x3 plus 5x4 equals 0. And what do we have in the third equation? So the third equation, we read that is 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 equal 1. What can we conclude from this last equation? Can the system be consistent? Could we have any solution? So a solution, a vector x1, x2, x3, x4, for which you have that is equal to 0. No, so there are no solutions. So basically, if in the echelon form you have a column of the form 0, 0, 0, 0, and then the last entry is not 0, then you can conclude that the system is not consistent. So you use the echelon form to first you reduce your system to the echelon form, your equation, the equation associated to your system to the echelon form. If you have a row that has this form, then you can conclude that there are no solutions. The system is inconsistent. What about the reduced echelon form instead? So the reduced echelon form has, we said, 1 in the leading entries, and above the leading entries I have 0. So the leading entry 1 is the only solution, the only non-zero entries inside the system. And we can use the reduced echelon form to actually deduce the solution of the system. So in this very simple case, the matrix has basically the simplest possible form. So it's again our vector B. And if we read the equation associated to this system, we have x1 is equal to 2, x2 is equal to 3, x4 is equal to 4. So in this case, we have a unique solution that is the vector 2, 3, 4. So that's why the reduced echelon form is useful. And in the next slide, I kind of summarized the row reduction algorithm. So this kind of sometimes called Gaussian elimination. It has many names, but we want to reduce our matrix performing row operations. And so let's give some details. So we start, and somehow the input of our algorithm is a matrix that is the augmented matrix of a linear system. So the matrix of coefficient, and we add one column from the kind of known term, the vector B. And when we perform row operations, so what does it mean, these row operations? Row operations here, what are we allowed to do? These are called elementary row operation, and it means that we are allowed to interchange rows multiply by a scalar and add two rows together. So this operation, this is what we call elementary row operation, and they do not change the solution set. I mean, it's maybe here we don't have time to do all the details, but you can really convince yourself looking at the examples that if you have a matrix of a system and you only perform this row operation, the solution set will remain the same. That's why they are called elementary row operation. And we'll see some example of this kind of elementary row operation. So this is what you are allowed to do. You try to modify your matrix and put it into an echelon form, only performing this elementary row operation. Then when you have the echelon form, you can ask yourself whether the system is consistent or not. And if not, then you stop. There are no solution. And again, here, how do we understand if the system is consistent? Then we ask if there are rows of the form 0, 0, 0, and then the final element is a non-zero element B. So as in the example that we had in the previous page. So either the system is not consistent, there are no solution, or if there are, if there are solution, if the system is consistent, then you keep modifying your matrix, again, performing these elementary row operations to reach the reduced echelon form of A, from which you can deduce the solution of the linear system. And then you stop. You have found the solution of the system, and that was the goal. So we could try to do an example in practice of all this, the step of this row reduction algorithms. And then I really invite you to just keep doing other exercises. You can go to the references, pick another example of a linear system and trying to solve it. And I mean, it's really not hard. It might require a little bit of time to understand how to do the manipulation. Don't be careful in not doing mistakes when you're adding rows together and just getting the right number. But conceptually, that's really just a very easy algorithms. So let's see an example together. So we start from a matrix that is the augmented matrix of a linear system. So we have 3 equations in the variable x1, x2, x3, x4, x5. And then the final one is the column b1, b2, b3. So this is our starting point, the augmented matrix of a linear system. What do? We have to, the first goal is trying to transform this matrix into a matrix in the echelon form, performing elementary row operations. So we are allowed to interchange rows, multiply rows by a scalar, and adding 2 rows together, and a combination of these operations. So what is step 1? So remember, we want to get this kind of step-like formation. So we consider the leftmost non-zero column. So in this case, there are no zero columns. So this is really the first column for us. And the position at the top, it's called a pivot position. So I don't know if you are like, I don't know if you are English speaking or not. I mean, if you're a native speaker or not. Pivot has a meaning in English that means something like a structure that you can use to make a process working. It could be really a mechanical thing, kind of something under which the system rotates, but even metaphorically, it's something that you can exploit so that a process works. And this is exactly what we are trying to do. We are trying to have a pivot that we can use to let the algorithm proceed. And the position at the top is this pivot position. And so to be precise, what is a pivot position? Is a position that would correspond to a leading 1 in the reduced echelon form. So we are trying to here have a 1 in the end and have 0 underneath. And the first things that you want to do is really have a non-zero entry here. So you want to have a non-zero entry in the pivot column. And if necessary, you can swap rows so that you would get a non-zero entry here. And this would create a pivot. So a pivot is a non-zero entry in a pivot position. Let me stop for a second. I don't know if people have any question or this terminology of the pivot position, the pivot column. I don't know if it's something that you've heard before. Understood. Good. So what do we have to do? What is the next step now? We have to make a 0 into the pivot position.
We may interchange row 1 into row 3.
Exactly. So very good, Kurat. So that's exactly what we have to do. So we interchange the first and the last row, and that we get a new matrix. So here I just inverted, and now we have our pivot here. So then remember that we have to get this kind of step-like formation. So we want to create zeros below the pivot. So here we already have a 0, so that's good. We want to create a 0 here. And remember what we are allowed to do. We can multiply rows together. So we will multiply by a scalar, or we can add them together. So the elementary row operation that will allow us to create a 0 here is, for instance, taking the first, replacing this row by the first row minus the second. So here, this is my notation here. I'm replacing the row in here with the first row minus the second one. And if you do the operation, then you see that here I get 3 minus 3, so I get a 0. And then I have the rest of the coefficient. So then what do? Then you ignore the row containing the pivot. So this was our pivot, so we don't touch this row anymore. And we focus on the submatrix here that we get. So the one that I enclose into the blue rectangle. And here we would just repeat the step 1, 2, and 3. So we go to the leftmost column of the submatrix. So is this column here minus 2, 3. We consider a position at the top. This is the pivot position. It has a non-zero entries, so we have a new pivot. This time is minus 2. And a new pivot column, this one here. So what's the next step now? If we have to repeat all the operation, what do we have to do?
I have a question here.
Yeah.
May we have take common from the row 1, 3 to make pivot 1? At this stage, is it possible, or we do at after making the other value 0?
Sorry, say it again. I didn't understand the question. Could you repeat, please?
I am saying, like in row 1, 3 minus 9, 12, 9, 6, 15. May I take the 3 common in the row 1 to make the pivot 1?
I mean, you could do it now, or we could do it later. Yeah.
Yes.
So it's not necessary to do it now, because if you first want to arrive to the echelon form, for the echelon form, you don't have a requirement. And the reason is, if you arrive to find out that your system is inconsistent, then you don't want to waste time just doing operation if in the end you're not going to have solution, right? So especially if we think computationally, you want to tell your computer, you know, before doing an operation that might not be needed, so and might occupy memory space, first let's make sure that there are solutions. So first you want to arrive to the echelon form, and then you might rescale rows and find the one in the leading position.
Okay.
So Kurat, can you tell me what is the next operation if we just want to arrive to the echelon form of the matrix? Now that we have a new pivot and a new pivot column.
We may do adding row 2 and 3. Yes. Adding minus 2 plus 3, 1.
So we don't want to create a 1, we want to create a 0 here, right? Because first we want to arrive to the echelon form to have this kind of step-like formation. And so first we need to create a 0 here. And we could do that taking 3 times the second row plus 2 times the third row, right? So if we do 3 minus 2 plus 2 times 3 is a 0. So we can do that, creating zeros. This is the other elementary row operation. And in doing that, we are actually lucky we create a lot of zeros. And then we have 2, 8. So then we have another pivot. Even in the last row, we found our pivot. And we have 3 pivots position. So we see that this is a matrix in the echelon form. It satisfies all the requirements. So in this case, there are no non-zero rows. Every row is non-zero. And there are 3 leading entries. And we see that below the leading entries, we have 0, and every leading entry is like in a column that is to the right of the leading entry above it. So we have our echelon form. And maybe a good remark here is that the echelon form is not unique. I mean, I might, as you said, I could have decided to divide by 3 the first row, and I would still get a matrix in the echelon form equivalent to the other one. So the echelon form is not unique. It depends on the choice of row operation that you get. So here, we could also understand if the system is consistent or not, right? Is the system consistent or not in this case, this specific example? Is consistent. That's good, Laila. So we said that to understand if the system is consistent or not, we have to decide if there are rows of the form 0, 0, 0, and then only the last entries, not 0. And in this case, there are no rows of this form, so we conclude that the system is consistent. So it makes sense to actually look for a solution. So then we have to find the reduced echelon form in order to understand the solution of the system. And what do? We start from the rightmost pivot. So we start from this one. This is the rightmost pivot. And we perform row operation to create 0 above it this time. And then we want to repeat for every single pivot. And finally, if the pivots are not 1, then we rescale. So basically here, we want to create 0 here and here. So what do? We could add together the third and the second and the third row. And we could take, to get a 0 here, we could take the first row minus 3 times this one. And it's convenient to work somehow with the last row because here I have only 0. So the operation, the kind of computation that you have to do are much simpler, right? So we do that and we create 2 0 here, then we don't touch this side anymore. We want to create a 0 here because that's the other pivot that is left. And we could do that taking twice the first row minus 9 times the second row, and we create a 0 here. So now we have that above every pivot, there are zeros. The final things that we have to do is rescale to get 1. And that's what we do in the final step. We divide by 6 the first row, you take minus 1/2 the second and 1/2 the third one. And you arrive to have a matrix in the reduced echelon form. Is it clear to everyone how we arrived to the reduced echelon form?
I have a question here.
Yeah.
Why we are making 0 above 2 for fifth column? In
because
fifth column, 5.
This one?
Yes, this one.
Because
why
because that's a pivot, right? So the pivot is 1, 2, and 3.
Okay.
And we want to, the reduced echelon form says that the leading entries, so where the pivots are, should be the only non-zero entries inside in the column.
Okay. Either above or below. Either above or below 3.
Where somehow, I mean, we know already if we are in a matrix of the echelon form, we know that below there are zeros. So for the echelon form is enough to have 0 below. But for the reduced echelon form, you want to have 0 also above it.
Understood. Thank you.
So that's why you create zeros here. And basically then from here, we can read the solution of the linear system. And let's say that we take our reduced echelon form. We want to go back to describe the solution of the system. So here we have x1, right, corresponding to this position, minus 2x3 minus plus 3x4 is equal to minus 24. x2 is the minus 2x3 plus 2x4 is equal to minus 7, and x5 is equal to 5. So here there are 5 variables, but they have different roles. So the variables that corresponds to the pivot columns, so in this case we have 3 pivot columns, and the variables corresponding to the pivot columns are x1, x2, x5. These we call them the basic variables. So we are trying to express the solution of the system in terms of the basic variables. So x1, x2, x5 equals to something. And the variables that corresponds to the non-pivot columns, instead of what we call the free variable. Free because they are allowed basically to take any possible values. So depending on the values of the free variables, we would get the corresponding variable, the corresponding value of the basic variable. So the free variables are free to take any possible values, while the basic variables, the values of the basic variables depends on the free ones. So we could write it in this way. So x1, x2, x5, our 3 basic variables. So in the case of x5, we have a number, so that's really clear. But for x1 and x2, that depends on an expression that involves the free variables. This is what we call the parametric description of the solution sets. Parametric because it depends by 2 parameters that are exactly the free variables. So let me stop. This is kind of basically the conclusion. We arrived to the end of our algorithms, and we are now, we can express we can express the solution of the basic variables. Any questions? Is it clear what we are doing? Clear. Okay. Maybe let me ask you a question now. So here we have 5 variables, and we said that we can express 3 of them in terms of an expression that involves the other 2. So how many solutions do we have? We said that the system is consistent, but how many solutions? Do I have a unique solution? I have infinitely many solutions, says Laila. That's correct. Do we all agree? Or Laila, maybe can you elaborate a little bit and say why you said infinitely many? I mean, we have that basically we are free to choose the values for x3 and x4. We're free to choose them as we prefer. So I could choose 2 and 4 and I would get corresponding solution, but I could choose 5 and 6 and I would get a different solution. So I have infinitely many choices for the value that I can assign to x3 and x4. So I get infinitely many solutions. And to be precise, since it depends by the value, I'm free to choose the value of 2 parameters, it will actually be a 2-dimensional solution set, infinitely many of dimension 2. Here, so to be precise, geometrically, that's a plane, something of dimension 2. So we don't really have time to maybe enter too much into the details, but I can say here, so we have infinitely many solutions. We can assign infinitely many values to the free variable. And to be precise, the dimension of the solution set is 2, that is equal to the number of the free variables. So basically the solution set, the solution set depends on 2 parameters, so it's two-dimensional. So the number of parameters from which the solution set depends on. And so geometrically, it is a plane so the solution set is a plane in a 5-dimensional vector space. Again, more in the reference. So, any questions about the algorithm? Is the idea of the algorithm clear? What are the steps? What do we have to do? Okay, Kurat says it's clear. Great. So I will send you the notes, and maybe we could just conclude. I had prepared a few questions on Padlet, so maybe we could try to do that, and then maybe instead of moving to the exercise session exam, I suggest maybe we stay around 10 minutes now, and then we can conclude the afternoon. Exam?
Yes, okay, fine.
Solution. How many, so is the system consistent, and how many solutions do we have? So, so all the answer is correct. So yes, the system is consistent. How do we know that? We said that the system is not consistent only if there are there is a rows that is all zeros, and then so all zeros in the coefficient matrix, and then the last column of the augmented matrix is a non-zero. So if you consider the augmented matrix, it will be all zero and then a non-zero at the end. And so for the coefficient matrix, you would need having one rows that is all zeros, but we know that there is a pivot in every row. So a pivot is non-zero by definition. So we know that this cannot happen. So the system is consistent. And how many solutions? It's correct. There are infinitely many solutions because we have 72 columns and only 57 rows. So it means that necessarily there are columns that are not pivot columns. And this would correspond to free variables. And free variables are free to choose, free to take any possible value. So for all the infinitely many values of the free variables, we will get a different solution. And to be precise here, the dimension is 72 minus 57, so 15 dimensional. We have 15 free variables, so a 15-dimensional solution space. And I think this is connects also to to this question here. Whenever a system has free variables, the solution set contains many solutions, true or false. True, exactly for what I just discussed. So again, you can, if the explanation are not clear, just we are really a small group, so just unmute yourself and ask or use the chat. So the second one, assume that the last column of the coefficient matrix is a pivot column. Is the system consistent? No, not necessarily because an earlier column might not be a pivot. So these are not correct. So if if you know that here you're working with a coefficient matrix, and you assume that the last column is a pivot. So there might be some zero rows, you don't know, but at least then you have a pivot. So in the last column, there is a non-zero entry in a certain position. So it would mean that you cannot have a row of the form 0, 0, 0 times something non-zero. So if the last column of the coefficient matrix is a pivot column, then is consistent. And this does not imply that there might be column before that are not pivot column, but you don't really care about that. You might have free variables, but you don't care. And the other one, the third one, instead, if you work with the augmented matrix, then you cannot conclude anything. So here, yes and no. I mean, I see the answer, but basically the answer is we cannot conclude, because that's the last column of the augmented matrix. So even if there is a non-zero entry there, you don't know what it happens in the last column of the coefficient matrix. So you cannot exclude that you have rows of the form 0, 0, 0 and something non-zero. So you don't know, basically. Then consider 100 equation in 100 variables. Suppose that the elimination algorithm, so again, this row reduction algorithm, reduce the last one to 0 equals 0. What can you say about the solution set? So there needs to be infinitely many solutions, because basically that means that there is not a pivot. So you have at least one column that is not a pivot column. So there will be a free variables. And no one tried to invent a matrix with no zero entries. But basically an easy choice, it could be choosing a matrix that has, for instance, every entry is equal to 1. So every entry is non-zero. But as soon as you take the difference between two rows, then you would create a row that is all zeros. Or it's enough to choose any matrix from which you have that one row is a multiple of another one. The pivot positions in a matrix depend on whether row interchanges are used in the row reduction process, true or false. And I would say that actually it's false, because the pivot position does not depend on the pivot position. The position is always the same. I mean, you might, to get a pivot, a non-zero pivot, you might need to interchange rows, but the position where the pivot will be is always the topmost in the leftmost non-zero column. So the position doesn't depend on the row interchanges. This one we already discussed. And the last, suppose the coefficient matrix of a linear system of 3 equations, 3 variables as a pivot in each column, then does the system has a unique solution? And yes, the answer is correct. Yes, you have a unique solution, because you have no free variables, and then there are 3 equations, 3. So there are no free variables, so then you get only the value of the basic variables, so it's a unique value. So thanks a lot for engaging in the question and try to solve them. And as I said, I could try to leave them as it is. So if you have the link, you could go back and look at the questions later on. And are there any final comments or?
Thank you very much, Professor.
Great.
This was wonderful.
This was wonderful and I have enjoyed a lot.
Great, thanks a lot.
Okay, are there any questions or comments? Okay.